Hi everyone, my name is Connor Dempsey. I'm the Principal Electrical Engineer for Chiplytics. Today I will be discussing how to use the newest version of the Chiplytics Power Spectrum Analysis software, which is version 4. I'll talk you through downloading the software, installing the software, and then using the software. So first, we're going to go to chiplytics.io/download. And the password for this area of the website can be provided upon request. Now, once you get to the download page, you can download the user manual for version 4 of the software, and then you can also download the actual installers. So I'm on a Windows computer, so I will download the Windows V4.2. Now that the installer has fully opened, you can read through the license agreement. As long as you accept the agreement, you can continue. I'll create a desktop shortcut for easier access, and then I will run the installer. So I'll just launch the Chiplytics application from the installer menu. So we can see the application is loading. And at this point, you could sign into the application, which will give you access to uploading your chip information and your part information to our servers. Otherwise, you can run in the offline mode. So when the application first opens up, there's going to be a lot of blank space. This is anticipated, and we will begin rectifying this by actually going and creating the first part. So the part's going to be based on what the actual IC is that you want to test. In this case, I have a couple of quad 2-input NOR gates from Texas Instruments and from Toshiba that we'll be testing today. So the first part that I'll be testing has the part number of TC74HC02APF. So to create this part, I'm going to go to File, and then I'm going to go to New and then Part. I will enter the new part number, which is TC74HC02APF, and click OK. Now I can enter the manufacturer, which in this case is Toshiba. I can enter the package type, which is a DIP, and it has 14 pins. And in terms of a description, I will call it a quad 2-input NOR. Now that we actually have this part entered, we need to go and set up the test configuration. And we're going to do that by clicking on the default test configuration. And if we double click on it, the test configuration window will pop up. So you can see that we can name different signals. So in this case, I've got a signal called VCC. It will apply a 2-volt amplitude. So that's really a 0 to 2 volt peak-to-peak square wave. It'll apply it with an excitation frequency of 100 kilohertz, and then I need to tell the software which pins to apply it to. Since this is a 14-pin DIP, the top right pin, which is going to be the power pin of the DIP, is going to be on pin 40 of the ZIF socket that we're using, and then the ground pin is going to be on the 7th pin of the ZIF socket. In addition to setting all this information, I can also determine the number of samples to take. So that's the number of repetitions it'll take for each of these test configuration measurements. Additionally, I can tell it the number of times to actually average the data. So this means that it will capture everything that I just set in the test configuration, and it will capture it 50 times and average all that data for each sample that I have set. Finally, I can tell it the number of data points that I want. The maximum number is 8,000. And I can tell it the sampling frequency at which the oscilloscope is going to be sampling the excitation data on the PSA system. So at this point, we're nearly ready to test. However, as I mentioned during the installer, we're not actually ready to test the PSA system yet. We need to actually install the waveforms SDK from Digilent to run the power spectrum analysis system. And we're going to do that by going to the Help menu and clicking Download Waveforms. So this will take us directly to the Digilent site where we can download waveforms. When you do this yourself, you're actually going to first need to create an account and sign in. Once you've done that, you should see something pretty similar to what I'm displaying here, where you can download the waveforms SDK. In my case, I would download the Windows 64-bit. You may find that you need to download a different package depending on what system you're using. Once you've downloaded and installed the waveforms SDK, you can navigate back to the application, and now you can actually start creating your signature sets. So at this point, we're ready to actually capture a signature set. In order to do so, we need to first connect the Chiplytics Power Spectrum Analysis system to the computer that we'll be using. And additionally, you should already have the 5-volt adapter plugged in. So I will go ahead and plug in the Chiplytics Power Spectrum Analysis System. Right now, the system will remain unconnected, and it will do so until we begin to capture parts. And we're going to do that by first going to New and Signature Set, where we will input the part information. So in this case, that'll be the TC74HC02APF Toshiba part. It's still a DIP14 package, and we're going to use the default test configuration. I won't bother entering any tags, but I will enter that the vendor was DigiKey. I will also not bother entering date code or comments, but these things can be additionally recorded for your own notes. At this point, I will keep the Capture Signatures button checked as I'm ready to capture, and I can click Save. Once I do so, the Capture Signatures window should come up for the PSA system. Because the unit was plugged in, it automatically connects. In the case that it doesn't, you can always click on this button here, and that should wind up connecting the system if your system was unconnected at this point. As you can see, the unit number is pre-filled in with 1, and I won't bother entering any labels, so I can go ahead and load the first of the TC74HC02APF units. So I loaded the unit into the ZIF adapter, I released it, and while pushing down, I have locked the unit in place by closing the compression switch on the ZIF adapter. And back on the PSA application, I can click the Capture button. Now, the first thing that the Capture button will do is capture a series of null signatures that will be used for this entire signature set. Next, it's going to actually capture the power spectrum analysis response from this particular device. And you can see that in this View Signatures window that's just appeared. Now, as you can see, the capture window is already ready for Unit 2, so we can go ahead and capture that. And I will do so by releasing the locking switch of the ZIF adapter and removing the TC74HC02APF part. Now I can load Unit 2. I can lock it in place, and I can click the Capture button once more. And that will capture data for Unit 2. As you can see, that has also been plotted in the View Signatures window. I can also click on one of these units by itself, and if I go to Plot and Signatures, that should show that unit. Additionally, if I have both units selected, and I click on the Show Legend checkmark, when I go and plot the signatures, both of the signatures will appear with a legend displaying that at the time. Additionally, instead of using the Plot tab, you can click on one of the units with either a double click or a right click, and that should give you additional options to either plot the signatures, plot PCA or principal component analysis for that a series of signatures, or it would allow you to disable the unit, in which case it's hidden from any future signatures you show or PCA mappings you draw. Or finally, you can delete the unit should you find that you need to. Now I will reselect both units, I will have them both plotted with their legend, and we can continue capturing signals or signatures for this particular series of chips. And as you can see, after capturing 3 components, the principal component analysis plot pops up automatically. I will continue taking the data, and then we can talk a little bit more about what the PCA plot does and what we can do with it. Okay, so at this point, we have taken data for all 10 of the TC74HC02 APF chips. As you can see in the FFT spectra, all of these chips have pretty similar device responses. Additionally, what this FFT signature window allows you to do is you can change the noise floor. So I can deselect this particular option, which will no longer apply a noise floor to the spectra. I'll leave that on for now, however. Furthermore, you can also check this box for averaging samples. Now what that does is if we go back and double check the default, we told it that we wanted to take 3 samples per device with the averaging count at 50. If that checkbox is checked, that means we're actually taking 1 spectrum per device, which is effectively an average spectrum of 150 signals. So it's 3 samples times 50 averaging count for each of those samples. Finally, as you've been seeing me click on and off, you can show the legend. And then additionally, you can color the spectrum by signature set. So when we have multiple devices in here, which I will show you momentarily, you can select this option, and every device of the same signature set will be recolored such that every device in that signature set is the same color. Finally, you can use the compare against null, which is going to compare the PSA spectrum that you took relative to the null spectrum that was taken for that particular signature set. Now, to actually take power spectrum analysis data for a different chip, I have another quad 2 input NOR chip that I can insert into the PSA system. This chip was manufactured by Texas Instruments. It is a CD74HC02E quad 2 input NOR chip. And you can see that I've just inserted that into the PSA system. Before I can actually go and test that chip, I want to enter a new part for it, which I can do by going to File, New, and Part. This is now the CD74HC02E. And we can fill in the manufacturer. In this case, it's TI. This is also a DIP package with 14 pins. And once again, it's a quad 2 input NOR. Now, I can go and reselect the default test configuration for this particular part. I will use the same setup, so it'll be VCC as the signal name. You can name the signal whatever you'd like. I will use a 2-volt peak-to-peak waveform, so it's going to be, once again, 0 volts to 2 volts. That's applied to the device's power pin. I will use an excitation frequency of 100 kilohertz, and similarly for the previous device, the signal pin will be 40, the ground pin will be 7. I will continue doing 3 samples with an average of 50 each and 4,000 data points at a sampling frequency of 33.33 megahertz. Now I just want to show you an additional feature in this menu. You can set up multiple test configurations for a particular device. You can do that by either right-clicking on the test configurations that you have presently set up. So you can just click on the New button and that will set you up with a new test configuration. You can also go to File, New, and Test Configuration, which we can now call VCC1P5. So we're going to do a 1.5 volt excitation. And as you can see, the new test configuration has popped up. I don't need to bother naming the signal name in this particular case, and I can set the amplitude for that peak-to-peak square wave to be 1.5 with a excitation frequency of 100 kilohertz. I will continue using the 40th ZIF socket pin for the signal and the 7th ZIF socket pin for my ground. Additionally, for any of these test configurations, and I'll show it with this particular test configuration, you can actually apply multiple signals in a single test. Now these are going to be applied sequentially, so let me first set one up and then I can explain what exactly is going to happen. So I can right click on this pre-existing signal and I can create a new signal. We'll call this one VCC3P5 for a 3.5 volt signal applied on the VCC pin. So at this point, I'm going to set the amplitude of that signal to be 3.5 volts. I'll keep the excitation frequency the same in this case, and the pins are going to be the same because 40 of the ZIF socket is the VCC pin on the CD74HC02E chip, and I'll leave everything else about this measurement the same. Now, if I take this configuration and run it on the CD74 chip, it's going to first take all of the null spectrum when I create a new signature set. Then it will take data for the 1.5 volt test. Then it'll take data for the 3.5 volt test, and then it's going to do this for a number of repetitions defined by the number of samples you've set. So this test is going to first apply 1.5 volts, then it'll apply 3.5 volts, and then it's going to repeat that 3 times because we're taking 3 samples for any particular device that we are testing with this particular testing configuration. Now, so that I can compare apples to apples, I'm actually going to not run this particular test configuration. I'm going to run the default test configuration, as that is the same as the test configuration I used on the Toshiba Quad 2 input NOR. So at this point, I can go and with the CD74 HCO2E part selected and the default part selected, I can go and do File, New, and create a new signature set. So we're going to use the CD74 HCO2E part number. This is manufactured by TI and it's a DIP 14. The test configuration is not going to be the 1.5, but it'll be the default test configuration. I will once again not enter any tags, and the vendor was DigiKey. At this point, we're ready to capture signatures, so I can save this information. And now that I am here, you can see that the PSA system has wound up disconnecting. In order to reconnect the system, I'm just going to click on this button. And at this point, we have reconnected to the PSA system, and I can click the capture button. Now, since the sample's already loaded, the PSA system is going to first collect the null signatures. And once it's collected the null signatures, it will go through and use the test configuration, the default test configuration in this case, to capture the signature for this CD74 chip. At this point, you can see the FFT of the CD74 HCO2E's power spectrum plotted in the View Signatures window. And I can also compare it relative to the fast Fourier transform of the results from the TC74 chip by just selecting that part and then going to Plot and Signatures. Now you can see that these two signature sets are pretty close, which is to be expected as these two devices are very similar in nature. They are both Quad 2 input NORs. However, they were manufactured by different companies. We can now take all of this data and plug it into our principal component analysis chart. And we can do that by going to the Plot tab and clicking on PCA. Let me bring that particular window up. And let me now maximize the window. What you can see instantaneously is that principal component analysis, which is a method of basically reducing the dimensionality of a set of data, immediately is able to distinguish a large difference between the TC74 HC02 APF device and the CD74 HCO2E device. And this is evidenced by the fact that the primary principal component 1, is the main axis that separates these two sets of devices. Additionally, what we can see is that the explained variance, or the total variance that's been computed by running the PCA algorithm, is 99.74% with just 3 components. Now we can adjust all of these calculations by going down into this bottom selection area, and instead of computing the explained variance for just the 3 primary axes, we can instead select the button to compute the explained variance to reach a certain threshold. In this particular case, I can set the threshold to be something like 99.9 or just 99.5. In both of these cases, the principal component analysis will be run to whatever threshold that's been set. If I set that threshold to be higher, more principal components will need to be included in order to actually reach that explained variance. Additionally, what I can do in this window is I can choose to apply a noise floor or not. So by reducing the noise floor, you can see that even still, there's a large difference in principal component analysis between the Texas Instruments manufactured part and the Toshiba manufactured part. I can also choose whether or not to average all of those samples. So if you remember, we were taking 3 samples with an average of 50 per device. I can deselect this, and at this point I should have 3 times the data points, because now I have a single sample with an averaging count of 50 for every device I've taken. I can hover over any of these devices and it tells me what unit it is and also what repetition of that unit is any particular point. I will reselect this just to reduce the number of units that are being plotted. And finally, I have control as to whether or not I wish to show the legend. And last but not least, we have a couple of options, including setting the chart to be a two-dimensional chart. So at this point, we're just plotting along the principal component 1 axis and the principal component 2 axis. And finally, I can run clustering software. So the Power Spectrum Analysis app can run clustering to determine whether or not there are multiple clusters and the fittings of those clusters in the data that's been presented. And when you start clustering your data, you're able to compute things like the silhouette score of that cluster, the Davies-Bolden index, and then also the classification accuracy. In this case, because principal component analysis is so effective at separating these particular devices, we have a classification accuracy of 100%, and our silhouette score is close to 1, which would be anticipated for a good result, and our Davies-Bolden score is very close to 0, once again indicating that this is a good fit. Okay, so at this point, to export the data, we can click on File, Export Signature Sets, and in this case, I can export the data as either a JSON or a CSV. You can choose either. Both will have all of the metadata in the test configuration and various extra data about the PSA system while it was running that will be included in the data set that you choose, or the data format that you choose to download. In this case, I'll choose the CSV data, which I can then proceed to put into my downloads/Chiplytics data folder. I will select this folder, and at this point, the data should be saved there. And as you can see, we have 2 CSV files. I will open the larger of the 2, which should correspond to the signature set with 10 different signatures. And opening it in my Excel, I can parse the CSV data, and you can see that all of the metadata and all of the signals data has been included in this particular file for all of the devices and all of the signatures that were taken. So at this point, we have demonstrated how to download, install, and use the Chiplytics PSA application with the Chiplytics Power Spectrum Analysis system. I hope that this has been an informative video, and please do not hesitate to reach out to us if you wind up having any questions or running into any trouble. Thank you. Bye.